Okay, in this video, let's talk about the horizontal compression and horizontal stretch. Still the same thing. Let's start from the example. Let's do the example and get the idea. We do the similar example, the same example, but with a different explanation. We have original function f of x equal to ups value of x. Last time we studied g of x as 1/2 ups value of x, 1/2 times of ups value of x. We consider this as a 1/2 times of fx, and this time we move this ups 1/2 into the ups value of, and we consider this as f of 1/2 times x. Okay, so we put this coefficient 1/2 into the ups value function and combine it with x and consider it as a coefficient of x, not the coefficient of the function. Okay, so we want to study this property. Let's check. One, two, three, four, five, six. 1, 2, 3, 4, 5, 6. 2, 3, 4, 5, 6. We know that the graph of the ups value is the diagonal of the first quadrant and the second quadrant, first and second quadrant. Okay, this is ups value of x. And now let's look at the 1/2 x. So x is 1. When x is 1, you actually get 1/2. 1/2 times 1 is 1/2. 1/2, ups value of 1/2 is 1/2, so it's here. And when x is 2, 1/2 times 2 is 1. You evaluate 1. You evaluate 1, and you get this point. And when x is 3, you get 3 halves. So it's 3 halves. When x is 4, you get 2. So when x is 0, you have 0. This one is f of 1/2 x. And similarly, you do the same process for -1, -2, -3, -4. Get the opposite straight. Of course, you will have the same graph. This is dot. I should draw it as a dotted line. This is original function, the graph of the original function. This solid line is the graph of the new function. We have the same graph, but we have explained it in a different way. This moment, we talk about the horizontal stretch and compress. You see, in the horizontal direction, it's actually stretched. Okay, this is a horizontally stretched. Horizontally stretched. Stretched version. Horizontally stretched. You stretch it along the horizontal direction. And similarly, you have ups value of x, and your g of x as 2 times ups value of x, and again we put this 2 into the ups value, then it becomes f of 2x. F of 2x. And we do the similar graph. this dotted line is a graph of ops value function. And let's check. When x is 1, you actually get input 2. 2 times 1 is 2. So when x is 1, you get input 2. When x is 2, you get input 4. When x is 0, you get 0. So you just get... Oops, sorry. Yeah, I have my ruler. My son brought my ruler, so that's good. I have my ruler here. Okay. And for the negative one, you get you get 2, because ops value of negative 2 is 2. And negative 2, you get a negative 4. Ops value of negative 4 is 4. 0, 0. Okay. So we get this. The same graph. Now let's explain it in a different way. If you look at this graph along y direction, it's stretched, so it moves up. But if you check it along the horizontal direction, it's actually compressed. So it's a horizontally compressed version. Okay, horizontally compressed. Along this direction, it's squeezed closer. Okay, so this is a horizontal compression and a stretch. Let's give the conclusion. Conclusion. That's 2 conclusions. If the argument x of a function y equal to fx is multiplied by a positive number a, this is 1/2, this is 2, the graph of the new function y equal to f of ax, not f of a, f of ax is obtained by multiplying each x coordinate of y equal to f of x by 1 over a. The graph of the new function y equal to f of ax is obtained by multiplying each x coordinate of y equal to f x by 1 over a. Okay. horizontal, okay, yeah. A horizontal compression results if A is greater than 1 and a horizontal stretch occurs if A is between 0 and 1. Okay, if A is between 0 and 1. Okay, let's explain what it is. See here. For example, originally, this is 1, 2, 3, 4, 5, 6. And if we're trying to understand what this graph is, we multiply all the coordinates by 1/2. This becomes 1/2, 1, 3 halves, 2, 5 halves, 3. Okay, so multiplying each x coordinate by 1 over a. Now for this example, a is 2, so divide everything by 2. You get this. You get this. You still select this dotted line. You select the dotted line, but this is 1/2. It is 1. You see here. This is still the same thing. The y coordinate is the same. So when you get x equal to 1/2, y is equal to 1. X is 1, y is equal to 2. See, that's exactly the same thing. But you do this multiplication, you actually change the scale so that the x scale is different from y scale. The graph will look different. So that's not a good strategy, but it's a correct strategy. And the best way is that you just label the sufficiently enough the point. Okay. And in this case, again, I mentioned if this A is between 0 and 1, it's a stretch along the horizontal direction. If A is greater than 1, it's a compression along the horizontal direction. Okay? Okay, now let's see the example. So we have the graph. This graph, fx, has a graph. It's pi over 2, pi, 3 pi over 2, 2 pi, 5 pi over 2, 3 pi, 7 pi over 2, 4 pi. Okay, so we have this and then we have wave function up, down, up, down. Okay, this is wave function. The peak is 1, the bottom is -1. Okay, so we consider this at pi over 2 is 1, at 3 pi over 2 -1, 5 pi over 2 is +1, 7 pi over 2 -1. Okay, and all these are pi, 2 pi, 3 pi, 4 y has a value 0 at 0, 0. And what is y equal to 2fx? 2fx you do not change x, so you have to draw the same x coordinate. And because this a is greater than 2, it's a vertical stretch. You see here, this is a direct multiplication with the value. You have vertical stretch. So originally you have 1 here, and then it becomes 2. Here is -1, it becomes -2. Okay, so you're going to stretch it. It's like it's inflamed. So this becomes -2, and this is pi over 2, pi 3 pi over 2, 2 pi 5 pi over 2, 3 pi 7 pi over 2, 4 pi. Just horizontal stretch. Okay? B. If we want to sketch this whatever, if we want to sketch this f of 2x, for this f of 2x, the value does not change, so you still have 1, the -1. And then let's see here. This is 2, so the x coordinate is compressed by 2. Multiply x coordinate by 1/2, right? That's what the conclusion says. You multiply by 1/2. For me, I feel you just say do some basic sample point 0. X equal to 0, 2x is still 0, so the 0 point is fixed. The 0 point is fixed. Whenever you have a 0 value, it does not change. It does not change. Okay? I say 0 value means when x is equal to 0. X is 0. Okay? And then you get pi, it becomes pi over 2. Right? X is pi times, sorry. Let's say it's not become so. X equal to pi becomes 2 pi, right? And x is 2 pi, it becomes 4 pi. But fx has a domain from 0 to 4 pi. X is from the domain of f based on this graph is from 0 to 4 pi. So when x is 2 pi, you actually literally have 4 pi. So now your domain is compressed to 4 pi. It's compressed to 2 pi. Even though you only see 2 pi, but with 2 it becomes 4 pi. Okay, this corresponds to f of 4 pi. And this corresponds to f of 2 pi, 4 pi. And here corresponds to, this is a 3 pi over 2 times 2, it is f of 3 pi. And this pi over 2, it corresponds to f of pi because you multiply it by 2. And then you can see that f of pi over 4 is corresponding to f of pi over 2. For x equal to pi over 4, this is pi over 4, it corresponds to f of pi over 2. So it looks like this. You just compress the graph from 0 4 pi to 0 2 pi. You divide the x coordinate by 2. Okay, make it compressed. That's because this 2 is greater than 1. 2 is greater than 1 is horizontal compression. 2 is less than 1. less than 1 between 0, and it's a horizontal stretch. Okay, and when you have domain, remember the domain is also compressed. The domain is also compressed or stretched based on this number 2. Okay, so that's the graph of y equal to f of 2x. You just figure out the basic point, the special sample point, and also easy to determine. And then you label them in the corresponding position and make the similar graph. Okay. Here I labeled something like this. So I put 2 pi here, means x is 2 pi, but multiply by 2 you get 4 pi. So that's why this point corresponds to the value f of 4 pi with this coefficient 2. So that's a f of 4 pi. F of 4 pi is 0. So that's why we got a 0 here. 3 pi over 2 is 0, pi is 0, pi over 2 is 0. Okay? And pi over 4 multiplied by 2, I get pi over 2. So at this point, it will give you the value f of pi over 2. That's how I make this graph. Reflection about the x-axis and the y-axis. Let's compare those two graphs. Y equal to x squared. This is a parabola opening up. And y equal to negative x squared. It's a parabola that's opening down. Okay, so with this negative sign, you actually flip it down with respect to the x-axis. So this is what we call the reflection about x-axis. The graph of y equal to negative fx is the reflection about x-axis of the graph of the function y equal to fx multiplied by -1. The whole thing by -1. You just flip it down. Okay. That's easy stuff. So you directly put negative sign in front of the whole expression with the parentheses if you have several terms. Okay. For example, let's use the last example. Also, you have this wave function. If this is called fx, then what is negative fx? Negative fx, whenever you go up, you go down. Whenever you go down, you go up. So this is a reflection. Okay? reflection about x-axis, you put a negative sign directly. You put a negative sign directly in front of the fx. If we want to get the reflection about y-axis, if we put a negative sign for x, not for f of x, square root of x is 1 is 1, x is 4, 2, 3, 4. Square root of 4 is 2, square root of 0 is 0. So this is a square root of x. And it's only defined for positive numbers. It's only defined for positive numbers, okay? So this is square root of x. And square root of a negative x is only defined for negative numbers, because when x is positive, this is really a negative number. But when x is negative, negative x is positive. Okay? So when x is 0, is 0. When x is negative 1, negative 1 is 1. Square root of 1 is 1. When x is negative 4, you get square root of 4. So this is square root of negative x. You see, it's like the two wings of a butterflies. And this is a reflection about the y-axis. Okay. The graph of the new function, y equal to f of negative x. You directly put a negative sign in front of x. Y equal to f of negative x is the reflection about the y-axis of the graph of the function y equal to fx. Okay, you put a negative sign for fx, that's about x-axis. You put a negative sign for x, it's about y-axis, the reflection. So that's how the reflection. Okay, so we study stuffs. So far we have 3 types of operation or the transformation: shift, horizontal shift, vertical shift, compression, stretching, and reflection. Reflection about x-axis, reflection about y-axis. So there is a table on page 551. 251, not 5. 251. This table is very, very important. Okay? So on page 251, there is a blue table. Understand that table. Okay, now let's make some very complex function. Usually when I say complex, it just means you have a series of transformations. Okay, so let me see. Okay, so we have the function y equal to absolute value of x. Now we are going to have 3 steps. Shift left 2 units. Shift up 3 units. Reflect about the x-axis. Okay, reflect about the x-axis. First, fx is upside of x. Let's say shift left 2 units. Replace x by x plus 2. We have this. Shift to left. Shift up. We get this. Then we have the new function g of x. Let's not use g of x. We get the function y equal to ops value of x plus 2. Okay, that's our new function with input x. And then shift up 3 units. This is our new function. Every time after you shift it, it's not the original function, it's this function. This function, you shift up 3 units. We abuse the notation, but let's all keep step. Shift up 3 units, so fx plus 3. Now this is our new function. The function has input x. Keep in mind, it's very important that we have input x. And reflect about y-axis. Reflect about y-axis. About y-axis, have a negative x. When you have fx, you put a negative x. Okay, yeah. Okay, so be careful. Every step, after you do one shift, one transformation, you rename it. I rename it. After every step, I rename the function to be the new f. Okay, this is our new f. So every time, this f follows the original definition. This f follows this definition. This f follows this definition. Every time I use this process. Because you do this in the decomposed way, and every step is based on the previous step. So the previous step will be your original function, not the original function, just your previous step as your original function. Okay, let's try this. Example. Graph. Fx equal to 3 x minus 2 and plus 1. So how do we do it? We decompose it into several transformation. First we get our f, 1 of x. 1 of x has graph like this. So we start from this is a graph, a function in the library of the functions. That in that section you have library of functions, you have a reciprocal function. It has 2 branches. Okay, that's our new. That's our starting point. Second, we multiply it by 3. multiply the value by 3, it's a vertical stretch. Multiply value by 3, you get the vertical stretch. So when x is 1, y becomes 3. When x is 3, y becomes 1. Negative 1 is negative 3. Negative 3 is negative 1. Because this graph is it's difficult to see if it's stretched or compressed. This is a 1, 1. It's negative 1, negative 1. Okay, so you stretch it. Okay, and second, remember we are going to call this new one fx, and we are going to move it right 2 unit. If you don't want to copy this, it's okay. If you don't want to rename it, it's fine. But I prefer to rename it. Then I can directly see how do I apply this transformation. I put x minus 2 instead of x, so this x becomes x minus 2. It's shift right 2 unit. Shift right 2 unit. Okay? So this 1, 2, 3, negative 1, negative 2, negative 3. Sorry, this corresponds to this one, this corresponds to this one. And let me sketch it. Okay, when you have a negative 3 minus shift right, shift to right. Let's say, how do I get a shift to right? 1, yes. 1 point, it is negative 1. The value, 1x is 1, 1 minus 2 is negative 1. 1, 2, 3, 4, 5, 6, 7. Okay, so when x is 1, you get a negative 3. 1, 2, 3. This point is shifted to here. And when x is 0 is negative 2. Negative 2 is negative 3 halves. Negative 3 halves here. And when x is negative 1 is negative 3. Negative 1 minus 2 is negative 3. 3 over negative 3 is negative 1, yes. And this 2, vertical line 2, is this vertical y-axis. So, and then we get 1 is equal to 3. 3 minus 2 is a 1. 3 over 1 is here. Y-axis 2, 1, 2, 3. Here it's 1. So 1, 2, 3, 4, 5. This 5 is the value of show the value of 3 here, because you shift the 3 2 unit right, you get 5. Okay, so this is our new graph. Okay, and the final step, we call this f. Then we shift it up. So all the graph is shifted up 1 unit, vertically 1 unit. So this is a 1, 2. This 2. This vertical line is not moved. And here, when it is 1, 2, 3. When it is 3, it is shifted up. It becomes 4. 1, 2, 3, 4. When When it is 1, it becomes 2. And this x-axis, this line is shifted to this line. And here you get the -1. This is -1, -1, and 0. This is -1, -2, -3. -3 you shift it up 1 unit, is -2. Okay, so you lift this graph 1 unit up, you get this. You move this 2 units right, you get this one. Okay, so this is the required graph. In this process, we select to multiply the function by 3 first, and this is vertical stretch, and then we shift horizontally to right 2 units second. It doesn't matter. You can change the order. Okay. You can change this order. Okay. Next example. We want to graph function square root of 1 minus x plus 2. Square root of 1 minus x plus 2. Okay, so this part we see some difference. Okay, sometimes you have to be very, very, very careful. So we start from the first one, square root of x. We call it fx. Square root of x has a graph like this. 1, 2, 3, 4. 1, 2. At 4, it's a square root of 4 is 2. So if you want to draw 9, you just draw it longer. So 1, 2, 3, 4. 1, 2. Okay, and the second step. We want to apply negative 1, negative x. If we have f negative x, it's a reflection about, okay, this way, y-axis, 1, 2, 3, 4. This is -1, -2, -3, -4. -1 is 1, -4, -4 is +4. So, okay. And we call this is definition. We call it new fx. This is new fx. I'm going to start from here. And then let's check the difference and the reason I redefined it to be fx. I want 1 minus x. From this expression, if I get 1 minus x, how do I write this f, this new f? This should be written as negative x minus 1. You see, this one is your new f, a new x. Negative sign is a coefficient. Here you cannot say it is 1 minus x, because the input is x, then you have negative sign. This part, when you get the this f of x minus 1, make sure you only consider x, you do not consider its sign. This part, there's no sign. Okay? So this one, if you ignore the sign, you see you only have x minus 1. That is your x, the change of x. This is a very, very weird place. whenever you have the coefficient and you have some addition subtraction about x, you have to factor out the coefficient. For example, if you have square root of 2x plus 3, how do I determine the horizontal shift? I have to write it as 2 times x plus 3 over 2. And this is your horizontal shift. The coefficient cannot be combined with x. Okay, so this is the horizontal shift, is shift left. And here is a similar thing. This negative sign is also the coefficient. You factor out the negative sign and you get x minus 1. Negative of x minus 1. So f of x minus 1. So x minus 1, you're going to shift right. Right? You're going to shift right 1 unit. -1, -2, -3, -4. Oh, sorry. I rescaled too bad. -1 is here, -2 is here, -3 is here, -4 is here. -1, -2, -3, -4. And 0. And we shifted 1 to the right, so 1 is here. 3 is 2. Sorry. 0 is shifted here. -1 is shifted to 0. And -3 is shifted to -4. So see, the graph is shift right 1 unit because it's x minus 1. And then plus 2. Plus 2 is easy. This is your new f. Again, that's a reason every time I want to rename it. So fx plus 2. Plus 2 just shift 2 units up, vertically up. 1, 0, -1, -2, -3. 1, 2, 3. So shift up 2 unit. My bad. I'm sorry. 2 unit. 2 unit. 4. 0. 2 unit is here. So 4 is here. It's this way. I still keep 1 in my mind. This is 2 unit. This is wrong. My bad. I'm sorry. Okay. So you shift up 2 unit, and it's not in. You just only get the part of a graph. Okay, so be careful about this step. This is the most tricky part about transformation. This is the most tricky part about transformation. Whenever x has coefficient, x has a shift, you have to be extremely careful. In all the previous examples, check that. In some example like this, it is easier. It doesn't matter how you shift it because this x has no coefficient. Okay? So for this kind of thing, you can do whatever shift, and it's straightforward to see what is the shift about x. But whenever you have coefficient, this is another example. Whenever you have a coefficient, you have to and you must factor out the coefficient. Okay? So let me see. This type of problem, it has exercise on page 255, problem 60, problem 59. For these two problems, you have to be careful about the shift. What is the unit? What is the direction? Okay, so other problems you don't worry about the shift, the unit, and the shift, but these two, 59, 60, those two problems, you have to figure out the correct quantity and the correct direction. Okay, and keep in mind the order about those steps matters in most cases. In some special case, for the special examples, for the simple examples, you can change the order. But for most of the examples, if you fix one order, you must clearly write down what is the next transformation. Okay, and that is the reason I want you to rename the function, because, for example, here your new function is fx equal to negative x. You see here, when you change x, you only change this part, you do not change the negative sign. Okay, you do not change the negative sign. So here, if you put x minus 1, for example, if you want to compute x plus 1, what is your new value? It becomes negative x plus 1. It is negative x minus 1. So it's different from it. Okay, so you don't plus 1 here. This is your new function. This is your new expression. Right? So in order to get a plus 1, positive 1, this place has to be minus. X minus 1. Then minus minus, you get a plus. Anyway, be careful about this type of stuff. The exercise is 59, 60. Okay? Okay, so we finished this section 3.5, graphing technique. We have shift, compression, stretching, and reflection. So 3 types of transformation. Understand how do they change the graph of the function. If you have a question, ask me, send me email. Okay? Okay, cool, we stop. Thank you.